Example 2 in section 7.6, we've got this object here. It has this charge, so mass and charge. It's placed beside the positive parallel plate. If you didn't watch example 1's video, I kind of explain sometimes why we do this. So maybe go back and watch it. I also derived some equations that we're going to use in here. So I place this guy here. I know delta V, so that's the potential difference across these parallel plates, 120 volts. It's going to go flying across this way. The question is, how fast is it going over here? So let's call it V primed. So V over here, 0. What we know then is, we're kind of using conservation of energy. So we're going to say kinetic energy. Now I don't have the ability to say electric potential energy is K, Q1, Q2, because I don't really have a Q2, and then it's over R. But I don't have Q2. What I have is a set of parallel plates with a whole bunch of charges in it. So what I'm going to say instead is the kinetic energy at the beginning plus any work done, including work done by the force that the parallel plates put on this charge, that's equal to my final kinetic energy of that charged particle. I'm going to rearrange this, and I'm going to say work then is EK final minus EK initial. That's going to go over the other side. That's delta EK. Okay, so work is delta EK. We've seen this before, right? Work is just change in energy, and that hopefully should make sense. I'm actually going to kind of work with this line though. So work is EK final minus EK initial. EK initial, because that V is 0, that's going to go away. Okay, so the kinetic energy is only the final kinetic energy, that thing right there. The work done, again, from our last video, if you didn't watch it, 7.6 example 1, I mentioned that work is, if it goes all the way across, Q delta V. Now I'm going to make an argument that we actually need a negative sign in here. There's like a whole other video I could go through to kind of explain why. Anyways, kind of believe me for right now. Well, here, let me do it really fast. If I go back up to this one, let's say this. EK plus EE equals EK primed plus EE primed. If I bring EE's over to this side, I'm going to get this EE minus EE final, this EK primed, and I'm going to bring this EK over to this side. This thing here is our delta V, that's it, or not delta V, delta EK. That's what we have right here. This thing right here is initial minus final. I don't want that, so I'm going to take a negative sign out and make it final minus initial. This is negative delta EE equals EK. This thing right here I'm replacing with work. So it's kind of like the negative work is delta EK. That's where this negative sign comes from. Anyways, if that doesn't make sense, you can ask me, send me a message or something, and I'll try to explain it more. Believe me, we need this negative sign. Now, also in our Google Meet, we talked a little bit about this delta V. Okay, so there was some kind of chicken scratch notes that I took, and I posted them, and I also posted it along in our Google Stream. I posted it along with a sheet. It was like 7.6. I write it 7.6. It was something like, a lot of short forms here, conservation of energy, and then in brackets it said negative potential difference, something like this. You can look through that to see when is delta V positive and when is it negative. You are always going to be given it as a magnitude. It's always going to be given as a positive. But in that sheet, or in both of those things, I kind of went through the example where if you are heading towards a negative, this delta V is actually going to be negative. Okay, they're never going to give you the negative, but this delta V right here is actually negative 120 volts. Okay, so that's a bit of a pain. Let me come back to that. I'll sub in some numbers and then we'll talk it through a bit more. So that negative is out here. Q is 3 times E. That is 3 times 1.6 times 10 to the minus 19. Delta V, negative 120. Again, I'll talk about that in a sec. Mass, 7.4, 10 to the negative 25. V primed, that's what we're looking for. v primed squared. All right, the negatives can cancel out. I need that in order that I can do a square root. Okay, so there's my first tip off that I need a negative right here. Anyways, I do some math. I'm going to get v primed is 12,500. So let's say v primed is approximately 1.3 times 10 to the 4 meters per second. This is just speed, so that's how fast it's going when it hits the plate. Okay, let me come back to this negative sign quickly. Again, look at this sheet. It's up in our Google Drive, or I posted it in the stream as well. I think I put it in overheads if you're poking around in our Google Drive. They're always going to give me a delta V, the potential difference. They're always going to quote it as a positive value, but sometimes it's negative. Okay, so if it's negative, I put in the negative sign. I need that negative right there. Here's my kind of way to remember. If I'm going through and I'm solving this and I forget that I need this negative, or I don't realize I need that negative, I'm going to end up with a negative here, and I'm going to be trying to take the square root when I solve for v of a negative. If you find you're taking the square root of a negative, then most likely what's happening is you need a negative right there. Okay, so this is bad physics that I'm proposing to you, but if you find, boy, I'm taking the square root of a negative, you're probably pretty safe to just stick a negative sign in there to make it work. Again, if you really want to know where it comes from or when it should be negative, check out this sheet over here and it should answer your question.